As Allison said, I'm Buddy Bland. I'm the project director for the Coral project at Oak Ridge National Laboratory. And I'm going to talk to you today a little bit about our present and future leadership computers. So I'll be talking about what we've been doing with Titan, as well as our new Coral system that we'll be getting in 2017. So the mission of the Oak Ridge Leadership Computing Facility is really to deploy and operate the computational resources required to tackle global challenges. So we're providing literally we're trying to provide the fastest computing, world-leading computational and data resources for our users to meet their needs. We also want to provide a stable hardware and software path, and that's really an important thing because the applications that our users use last much longer than any one particular hardware platform. And so when we pick a programming model and a programming path for our users, we want to stay with that for a long time and scale that out for our users to use. And so you'll see that theme with our new system. We need to provide this most powerful computer because our users are trying to investigate systems that are really otherwise inaccessible. You can't investigate by just looking at them, experimentally in many cases. So from, at every scale, from things like galaxy formation and supernovas down to things the size of the Earth, to system sizes like automobiles, all the way down to nanomaterials. And then with our partners, our user partners, we want to deliver transformational discoveries in materials, climate, biology, energy technologies, and basic science. And that's really the mission of the Office of Science of the Department of Energy. Now, we all know that the clock rate scaling of processors has not really changed since about 2003, 2004. So we're not getting the clock speed faster on the processors. So in order to scale applications, we're having to scale the size of our machines. So we had a whole series of of upgrades of the machine called Jaguar that were based on AMD processors, CPUs, ultimately culminating in a machine that was about a little more than a petaflop, about 7 megawatts. It was the #1 machine in the world in 2009-2010 timeframe. At that scale, it was about 7 megawatts of power. We did a 10-fold increase in the peak performance and in the performance of applications on it with just a tiny increase of the power of the machine when we went to this hybrid GPU-CPU model, when we put in the Nvidia Kepler K20 processors in 2012, when we put in the Titan system. Our next machine that we're calling Summit will do another 5 to 10x improvement, also staying with the GPU model, and that's the Coral system that we'll be talking about. And then continuing that path, we expect to go to a peak exaflop machine in the 2022 time frame, going out in this area. And so we need to, and we're doing this with very, very powerful nodes. So we've increased the power of the nodes every single time, and we'll talk more about that as we go forward. So this is today's system. This is today's Titan system, 27 peak petaflops. Importantly, 18,000 nodes. And these nodes are about 1.5 teraflops peak. Total memory on the system, each node has about 38 gigabytes of memory combined with high-speed memory on the GPU and DDR3 memory on the Opteron CPU. And then a PCI Express version 2 link between the CPU and the GPU. And that's a bit of a bottleneck today. And we knew that when we installed the system Titan that would be a bit of a bottleneck. But we also knew that we needed to take this step. We needed to start getting applications to use this system because this was a power-efficient way to move forward and get high performance on our applications. It has Craze Gemini 3D Taurus interconnect, which has been a really very good interconnect. And we used Lustre, the high-speed file system, 32 petabytes and a terabyte per second of bandwidth on our system today. So this is today's machine, Titan. We've done great science. Our users have done great science with Titan. So everything from fusion energy, learning how to harness the power of the sun to create electricity, So C.S. Chang from Princeton Plasma Physics Laboratory has been working on understanding edge effects, which is really critical to how you are able to harness power out of fusion reactors. A company called Ramgen is looking at how you use turbo compressors that ultimately could be applied to carbon capture and storage to be able to compress CO2 into a liquid at a third of the cost of the conventional ways of doing this. Our Center for Advanced Simulation of Lightweight Reactors, CASTLE, is doing full-up simulations of the Westinghouse AP1000 nuclear reactor. And they've done successfully performed startup simulations, power-on simulations of these virtual nuclear reactors. So this is the first energy hub that the Department of Energy put together. And so we're doing simulations of full nuclear reactors on Titan today. I won't go through all of these, but climate science, earthquakes, being able to assess hazards of earthquakes by doing by doing high frequency simulations of the Earth movement. So all of these are very important aspects, are very important scientific problems that really require the size of a machine like Titan and the performance of a machine like Titan to be able to move forward. So where do we go from here? Well, we want to provide a more powerful machine for the DOE Office of Science and for our users for the 2018 through 2022 time frame for our Insight users and ALCC users, which are our two main allocation programs. So we formed a collaboration with Oak Ridge, Argonne, and Livermore called Coral to do a single acquisition with several benefits, and I'll talk more about this here. So the collaboration of Oak Ridge, Argonne, and Livermore, the acronym CORAL, the objective is to procure 3 leadership computers using one RFP. So a single RFP issued by Lawrence Livermore for systems greater than 100 petaflops, greater than 2 gigabytes per core of main memory, local NVRAM. But most importantly, what we're really looking for is we're looking for performance 4 to 8 times the performance of either Titan or Sequoia, the number 2 and number 3 machines on the top 500 list today. So the machine at Oak Ridge as well as the machines at Lawrence Livermore. Our approach, a competitive procurement, a single RFP. We'll buy 3 machines off of this. That will be the Oak Ridge and Argonne will, because we're both Office of Science laboratories, will select 2 different architectures because the Office of Science wants to maintain 2 different architectures going forward. And then Lawrence Livermore from the NNSA, the National Nuclear Security Administration, will then select one of those 2 architectures for their machines. We'll issue 2 R&D contracts for those 2 architectures, and then 3 build contracts for each lab will issue their own build contract. And on Friday, we're announced the Livermore and Oak Ridge contracts for the machines, and I'll tell you that in just a minute. The Argonne contract is still under negotiation, will be announced hopefully soon. Okay. There's really 2 paths going forward. Today, if you look at the systems, there's 2 machines. There's these hybrid multi-core machines like Titan, and then there's many-core architectures like Sequoia and Mira, which are basically IBM Blue Gene systems. Here we've got small numbers of very powerful nodes. We've got multiple levels of memory. The many-core architecture has tens of thousands of nodes. The nodes are somewhat less powerful, but you've got many, many more of them as you're going forward, and homogeneous nodes as opposed to heterogeneous nodes. So these are kind of the architectural paths that we've got today, and you might expect that you would go forward. You would see these architectural paths continuing. So here's the machine that we have selected for our architectural path at Oak Ridge. And this is the machine that we're calling Summit, and it will be delivered in 2017. It's an IBM Power 9 Nvidia Volta system using a Mellanox interconnect. All of those companies are part of the Open Power Foundation, founding members of the Open Power Foundation. It'll have at least 5x the performance of Titan today on applications. Approximately 3,400 nodes. Now that's really different from what with Titan, and I'll show a table at the end that shows a comparison of Summit and Titan. But many fewer nodes than Titan has. Multiple IBM Power 9, multiple Nvidia Tesla Volta GPUs on each node. The CPUs and GPUs will use this NVLink architecture that you've heard about at this show and at the GPU Technology Conference. This is a really key piece of technology. It gives a cache-coherent, very, very high-speed interconnect between all the memory on the node so that the CPUs can access the high-bandwidth memory on the GPUs can access the DDR memory on the CPU, all at very, very high speed. So this is a critical piece of technology. In addition, there'll be 800 gigabytes of NVRAM that can be either a burst buffer or directly accessible memory, extended memory on each and every node. So this node, instead of 1.5 teraflops that we have on Titan, this is over 40 teraflops of peak performance on a node, so an extremely powerful node. The interconnect is a dual-rail Mellanox EDR InfiniBand with a full non-blocking fat tree interconnect, and then the file system is IBM's Elastic Storage. That's their new name for what most of you refer to as GPFS. A terabyte per second of I/O bandwidth and 120 petabytes of disk capacity. So that's the snapshot of what the new machine's going to look like. A little bit more about NVLink and the stacked memory, the high bandwidth memory. So this is a slide that Nvidia used at their GPU Technology Conference back in the spring. If you want more information about this, I encourage you to talk to Nvidia directly because they can give you more information under NDA, or you can look at the slides from the GPU Technology Conference where they do give you a little more detail. NVLink is this really high-speed interconnect, 5 to 12 times the PCI Express Gen 3. Now remember, Titan's using Gen 2, so this is even faster comparison than what we're seeing on Titan today for being able to move data. And then, of course, it supports the power CPUs. So this is something that's being built into the power silicon as well as to the Nvidia silicon. So this is a very high-speed link. And then this stacked memory using the HBM high bandwidth memory standard. It's 4 times higher bandwidth, order of a terabyte per second of bandwidth to the GPU, and then through the NVLink to the entire system. 3 times larger capacity, 4 times more energy efficient per bit than other technologies. So these are really critical technologies to getting the performance out of the system. So what does the software look like? We talked about the hardware. How am I doing here? Doing good. Okay. From the software environment, our programming environment, I told you at the beginning that it's really important that the applications last longer than the hardware, and it's really important that we be able to move those applications from system to system. So we need our software environment to look as much like our software environment on Titan. We want to carry that over to Summit. So we're doing quite a bit of work to do that. So our compilers today, and going back to 2005 on the Jaguar series of machines, our primary compiler has been PGI. We're going to have the PGI compiler available for our users. Of course, we'll have other compilers available, but our primary compiler that our users have been using will be available, as well as all of these others. The libraries will have IBM's libraries. Will have other libraries that we are using today that are available on Titan today. The debuggers, we've worked very closely with Alinea to scale out the DDT debugger as well as to make it work on the Nvidia GPUs. We will have that on this new system as well as other tools. Profiling, we'll have IBM's tools. We'll also have the Vampire tools, which we have on Titan today. Our system software, it'll be running Linux, it'll be running GPFS, we'll be running IBM's platform computing LSF for our workload manager, and then the cluster manager XCAT for the system management tools. So this is a chart that compares Summit to Titan. I'm not going to go through all of the details on this, but you can see the number of nodes, dramatically smaller than Titan, but much more powerful nodes. you can see that we've got the NVRAM that we're adding in here. This is a new technology that many machines will start having at the high end, and really gives you a lot of capability for smoothing out the burst buffer. Gives you the capability of smoothing out the I/O. The Mellanox interconnect, quite a bit faster than today's interconnect. It's a non-blocking fat tree instead of a 3D torus. And the peak power consumption. So we're 5, perhaps as high as 10x in the performance. We're only 10% higher in power consumption. And this is peak power consumption. We're likely to be somewhat less than that in actual day-to-day power consumption.